Welcome. This demonstration presents proof of concept number 9 from the MARE project, DDoS attack detection and mitigation from X-Edge. MARE is a smart networks and services joint undertaking project under Horizon Europe, addressing the cybersecurity challenges of beyond 5G and 6G networks. In this video, we walk through the motivation, architecture, live demonstration, and key results of this PoC. The primary objective of PoC 9 is to detect, classify, and mitigate distributed denial of service attacks originating from compromised user equipment at the extended edge of 6G networks. As edge environments grow more heterogeneous, spanning mobile edge clouds, IoT devices, and private infrastructure, they become increasingly exploitable as entry points for attacks directed at the 6G infrastructure. The attack vectors we address include volumetric floods, SYN, UDP, ICMP, and GTPU, as well as signaling storms targeting core network functions, such as the UPF and AMF network services. These are grounded in MITRE fight techniques and aligned with 3GPP-TS 23.288 abnormal UE behavior analytics. The security guarantee we pursue is network availability, ensuring 5G and 6G services remain operational even under attack, with a detection F1 score target of at least 0.90, a mean time to detection of 2 seconds for volumetric attacks, and an end-to-end detection to mitigation latency of under 10 seconds. The MARE contribution brings together the CEPE security engine, paced for pre-assessment via the network digital twin, a cloud-native pipeline of DDoS, closed-loop enforcement through Adaptive Security Policy Orchestrator ASPO. The validation scenario involves 2 partner testbeds, NCSR Democritos, operating an Amersoft callbox as physical 5G RAN and core paired with a network digital twin built on Uransim and Open5GS, with telemetry collected through Prometheus, Grafana, and Wireshark, and Space Hellas, contributing complementary beyond 5G infrastructure. The scenario involves 2 UE populations, benign UEs generating normal high-throughput TCP traffic and malicious UEs acting as compromised edge nodes silently launching volumetric DDoS floods against network services. The execution unfolds in 2 phases. First, the network digital twin safely generates an extensive synthetic dataset of benign and attack traffic covering SYN, UDP, ICMP, and GTPU flooding across N3, N6, and N9 interfaces, used to train the LSTM classifier without any risk to the live network. Second, the trained model is deployed on the physical infrastructure, where malicious UEs inject real DDoS floods and the classifier detects and classifies attacks in real time. The technical implementation is built around 2 groups of DDoS. The monitoring DDoS, consisting of the NWDF implementation, metrics collector, and metrics storage database DDoS, collect 5G core and RAN metrics via NWDF following 3GPP-TS 23.288, Prometheus system-level metrics, and pack-to-trace-derived flow features from N3, N6, and N9 interfaces. The security DDoS, the anomaly detection and classification engine, and fast API interface DDoS, run an LSTM classifier that distinguishes benign traffic from SYN, UDP, ICMP, and GTPU flooding attacks, exposing detection results as structured JSON alerts to downstream MARE components. Both groups are implemented in Python with TensorFlow and Keras, using Smote for class imbalance handling and deployed as containerized services. The DDoS are composed into 2 security functions within the MARE security plane. Security Function 1. The DDoS Anomaly Detection and Classification SF is the primary deliverable of Iteration 1. It implements a full pipeline where NWDF and Prometheus telemetry flows through the metrics collector and metrics storage database into the anomaly detection engine, whose outputs are exposed as real-time alerts through the fast API interface. Security Function 2, UE behavior fingerprinting and mitigation, is planned for Iteration 2, correlating NUDAF-derived UE session patterns against baseline profiles to identify compromised edge devices and trigger closed-loop mitigation through ASPO. The broader MARE security plane components involved include CEPE for security function hosting, PASTE for NDT-based pre-assessment, and the network digital twin formed by Uransim and Free5GC or Open5GS. 3 primary KPIs govern this PoC. First, the attack detection rate must reach at least 95% for volumetric floods and 90% for low-and slow patterns, validated against Wireshark ground truth. Second, the mean time to detection must not exceed 2 seconds for volumetric attacks and 5 seconds for stealthier patterns. Third, the detection to mitigation time, targeted for iteration 2, must not exceed 5 seconds for policy propagation and 10 seconds for full-flow rerouting, while ensuring service continuity throughout. Additional benchmarks include an AIML macro F1 score of at least 0.90, already exceeded in our preliminary results, a false positive rate below 25%, and a network digital twin fidelity score, measured as dynamic time warping distance, below 15. In iteration 1, 3 implementation stacks have been successfully deployed. The monitoring stack collecting multi-layer telemetry via Prometheus, TupDump, PSTAP, and NWDF across N3, N6, and N9 interfaces. The data stack providing persistent aggregation through the metrics collector and metrics storage database DOTs. And the AIML stack delivering the LSTM classifier trained on the NCSRD DDos dataset and the fast API interface. Initial results are compelling. The LSTM achieves 99.69% accuracy with a macro F1 score of 0.9879 on a 5-class test set, with cross-fold validation confirming a stable macro F1 of 0.93. Attack experiments across all flood types produced clear traffic anomaly signatures immediately observable in Grafana, while network digital twin fidelity was confirmed through dynamic time warping analysis, validating the NDT as a reliable training environment. This slide shows the NCSRD testbed architecture. The upper layer is the network digital twin, your ransom for the radio network paired with free 5GC or Open 5GS for the core, with telemetry exported to Grafana, Prometheus, and Wireshark, and a management and orchestrator framework, Katana, handling network service management and orchestration. The lower layer is the physical network, Amorosoft RAN connected to the Amorosoft 5G core and NWDF, with telemetry collected via the Amorosoft web interface. The NDT mirrors the physical network behavior at all times, allowing us to train AIML models, test attack scenarios, and validate mitigation actions in a safe virtual environment before any enforcement reaches live infrastructure. Zooming out to the full MARE platform view, we see how the NCSRD testbed integrates into the broader cybersecurity architecture. At the bottom, the abstraction layer, numbered 1, handles telemetry collection feeding structured data to the cybersecurity core. The cybersecurity core houses PASTE for pre-assessment via the NDT, the CEPE security engine hosting our security functions, and the adaptive security and privacy orchestrator with reinforcement and policy learning feedback loops. The bottom pipeline illustrates the specific PoC 9 chain, anomaly detection and classification feeds from NWDF through Prometheus into AIML models, driving the CEPE security decision engine. We now present the live demonstration on the network digital twin. This slide captures a GTPU flood attack in progress, executed using the DDos attack framework targeting the core network UPF. The terminal confirms the attack is running, a GTPU flood directed at the UPF, while the TupDump output on the Open 5GS node captures the resulting packet stream on UDP port 2152 in real time. On the right, the Grafana dashboards immediately reflect the attack impact. UPF CPU utilization climbs sharply from around 30% to a peak of 85%, while total traffic volume surges in parallel. This controlled NDT experiment is the foundation of our dataset generation pipeline, producing the labeled attack traffic that trains our LSTM classifier before any deployment on the physical infrastructure. This slide shows the GTPU flood attack executed on the physical infrastructure. On the top right, a Raspberry Pi attacker device runs the GTPU flood script targeting the Amorosoft physical core at UDP port 2152, injecting approximately 2,000 packets per second. On the bottom right, TupDump on the Amorosoft node confirms the flood is being received, a dense stream of GTPU tunnel packets traversing the N3 interface and hitting the physical core in real time. The Grafana dashboards on the left reflect the immediate impact. UPF CPU utilization climbs from a 30% baseline to a peak of 85%, while total traffic volume surges correspondingly before tapering off as the attack concludes. This captured telemetry, consistent with the attack signatures previously observed in the NDD, is precisely what our pipeline ingests and passes to the LSTM classifier for real-time detection and classification. Moving to the experimental results, these two graphs present the GTPU flood traffic analysis side by side for the physical network and the network digital twin. Each colored line represents the throughput of an individual UE for benign users and 2 malicious users, measured in bits per second. The physical network shows the characteristic DDoS signature. Benign user throughput gradually degrades as the malicious users, indicated by the dotted lines, begin flooding, with clear network recovery once the attack concludes. The network digital twin replicates this behavior with high fidelity. The same throughput degradation pattern, the same relative timing of attack onset, and the same recovery trajectory are all faithfully reproduced in the emulated environment. This confirms the NDT's suitability as a safe and reliable training and validation environment for our AI/ML models. This slide provides quantitative confirmation of NDT fidelity under GTPU flooding conditions. The left chart shows the aggregated benign and attacker throughput for both the physical network and the NDT on the same axis. The benign traces, physical and NDT, track each other closely throughout the entire window, while the attacker traces rise and fall in near-perfect synchrony during the attack period, demonstrating that the NDT faithfully reproduces both the magnitude and timing of the GTPU flood. The right chart shows the dynamic time warping cost matrix between the physical and NDT time series. The warping path hugs the diagonal tightly across all experiment duration, yielding a DTW distance of 9.6, well within our target threshold, quantitatively confirming the NDT as a high-fidelity mirror of the physical network under attack conditions. It must be mentioned that similar encouraging results are observed for SYN, UDP, and ICMP flooding attacks. Our detection engine is based on a long short-term memory recurrent neural network implemented in PyTorch. LSTM networks are specifically designed to capture complex temporal sequence patterns, exactly the kind of time-varying statistical signatures that distinguish normal mobile network traffic from DDoS flooding behavior. The architecture is a stacked two-layer LSTM with 64 hidden units per layer and dropout regularization at 0.2 to prevent overfitting. Each layer processes raw per-second IP traffic statistics, features such as packet size, inter-arrival time, flow byte count, source and destination ports, and protocol type, extracting high-level behavioral features from the raw telemetry stream. To address the natural class imbalance between the abundant benign traffic samples and the relatively rare attack instances, we apply SMOTE resampling combined with stratified five-fold cross-validation during training. This approach synthetically balances the minority attack classes while simultaneously removing borderline noisy samples, producing a robust and generalizable classifier that performs reliably across all 5 traffic classes. The classification results demonstrate the strength of the approach. On the full test set of 7,030 samples, the model achieves an overall accuracy of 99% and a weighted average F1 score of 0.99, near perfect discrimination between all traffic classes. The per-class breakdown is equally strong. Normal benign traffic achieves an F1 score of 0.99 with perfect recall of 1.0. SYN flood achieves 0.89 F1, the most challenging class given its structural similarity to normal TCP traffic. UDP and ICMP floods achieve 0.92 F1 each. And GTPU flood achieves 0.92 F1 with a precision of 1.0, meaning no false positives at all for GTPU classification. The macro average across all 5 classes is 0.93 F1 score, with a macro precision of 0.98 and a macro recall of 0.89. These results confirm that the LSTM model meets and substantially exceeds the PoC 9 detection accuracy requirements and is ready for integration with the CEPE detection engine in the MARE platform. Our future work will focus on 3 areas: completing the anomaly mitigation engine SF for fully closed-loop enforcement via ASPO security playbooks, hardening the AI/ML models with extended datasets, and expanding attack scenario coverage to include NAS-level floods targeting AMF and NRF, as well as hybrid multi-vector attacks. For Iteration 2, the primary goals are full integration with the MARE cybersecurity core for automated security function composition and pre-deployment pace assessment, SSLA policy compliance validation, federated AI/ML model training across NCSRD, SPH and UPC testbeds, and deployment of the UE behavior fingerprinting security function. Thank you for watching this demonstration of PoC 9 from the MARE project.